Alright, welcome back to PA Academy. So we are still talking about nodal analysis. So here we are looking at example 3. So if you mix the other parts, you can check the description of this video. You'll find a link to the other parts where we've done 2 other examples and then introduction under nodal analysis. So now let's look at these circuits. Unlike the previous examples that we looked at, we just have 2 meshes, but now we are having 1, 2, 3, and then we have more elements in this particular circuit. So here we are, what exactly we are looking for is we are looking for the value of VA and VB. That means, so the question is asking us to find the voltage at node A and the voltage at node B. So the voltage at node A, that means these 2 nodes. So this is a node here, this is a node. And don't forget, I've said earlier, what is a node? A node is a point of connection, where 3 or more elements, they are points of intersection. So if you are still not clear on the difference between a node, a mesh, a loop, and branches and all these things, I've done a video explaining those terms. Alright, now let's follow the step I gave earlier on how to solve nodal analysis. I said the first thing you do is to identify how many nodes do you have in that particular circuit. So I want you to look at this circuit, for example. How many nodes do you think are in this circuit? So take your time to look at it closely and just write it down. How many nodes do you think we have in this particular circuit? Alright, so once you have done that, then you pick one as your reference node. So the first question, how many nodes do we have? Now the question has gone far to tell us that we should look for the voltage at this node here, this node here. So that means this is a node, this is a node. So another node that we are having here is a combination of this. This is a node, because this is a point of intersection. This is a point that is connecting 1 to this and this. So the fact that there's nothing here, so don't make the mistake of, so let me just redraw this diagram. Let me just draw the lower parts. So here we are having this, and then we are having this. We are having this. Okay, we are also having, and then towards the end we are having this. So I'm just drawing the lower parts. So don't just make a mistake of saying this is also a node and this is a node. Is that clear? So there's nothing in between here. There's nothing here. So it's just like having everything meeting at this point. Just like having it, let's just say we have everything meeting at this point. So that's what is happening here. All these things from this place like this is taken as a what? As a node. So there are more examples like that can be or question that you might come across that might be confusing like that. So don't make the mistake. You look at it closely. This is just like having a wire to make the diagram neat. Exactly. So it's the same thing as having a diagram look like this. Let me just draw it out in full. So it's just like having the diagram like this. Let's say. And then you have this. And then you have from here. And then you also have, so you can see that everything they are meeting here, it makes this place a node, and that's the same thing that is happening here. So the difference between these two is the fact that this is just drawn, they are more spaced, unlike here where everything is just coming straight, instead of what we are having here. Maybe before they come like this, this one should come straight like this, exactly. So this is also the same thing. The only so that makes this place a node. This node that we are having here, this is what I circle here like this. So this is a node. Alright, so I hope that is clear there. So don't make a mistake of calling this particular point a node and this is also a node. So they are together, that is what makes it a node. Alright, so now, since we've been able to identify the nodes, this is one, this is one, this is the third one. So this one is what we are going to pick as our reference node, and then we'll take it to be 0. So we haven't done that. We've identified the node, we've picked our reference node. Now let's give it some random direction for our current before we apply Kirchhoff current law. So for this particular circuit, you can choose whatever current direction you want to pick. It's left to you. Once you do that, we'll still arrive at the same answer. So for this now, I'm just going to pick something like this for my own current direction, and then for this particular node, I'll just take it to be like this. So what does this mean? So that means for this particular node, we have just one incoming current, so that means current is coming through this one and it is leaving through these two branches. That means here and here they are outgoing. Why for this we have two incoming here, incoming and one outgoing here. So now what we do is, since we are having two nodes, unlike the other example where last two example we had just only one node that we are making reference to, apart from the reference node we had just one, but now we are having two nodes. I'm not talking about this now. We are having two nodes, so what we do is we pick it one after the other. So what we are going to say is now is apply Kirchhoff current law to node VA. That means to this node. Is that clear? So what do? We look at what are the incoming currents. So from here we have, now there's no need for you to start doing something like this. Unlike the previous example, this is another thing you have to pay attention. There's no need to be having 0 minus VA, okay, then over maybe over 4 or whatever. No, because if you look at it closely, we already have a current on this part. On this particular branch, there's already a current of 12 amp. That means whatever current that is here is the same current that is flowing through this 4 ohms resistor. So you can go ahead and write it as 12. I hope that is clear. So that is the only current that is entering into this node VA. Don't forget, that is what we are considering now. Apply KCL to node VA. This is the node that we are putting into consideration. Alright, so 12 then that equals 2. So let's look at the outgoing current. So for the outgoing current, so let's start with this. From this point VA to the reference point. So since it is from this VA to the reference point, we are going to be having VA minus 0. There's no that in then, divided by the resistor, which is 10 ohm resistance, with a resistance of 10 ohms. Another outgoing current which will now be plus. Now the place on the direction we pick, that means from VA to the next node, which is VB. So we are going to be having VA minus VB. Now if you look at it closely, you see that there is a voltage in between it. So let me add the polarity. The longer side is positive, the shorter is negative. So based on this direction, that is from positive to negative, that would be minus 20. On this same, between this node VA and VB, we also have a resistance of 5 ohms. So that will be divided by what? By 5. So now we've been able to apply KVL to this node. So let's just simplify what we are having here. So this is going to be 12 equals to, so this this is just LCM, that will be 15. Sorry, you can just use 10. That's 10. So we are going to be having VA 10 divided by 5, that's 2. 2 multiplied by everything that we are having here. So we are going to be having plus 2 VA plus 2 VB, and then multiplied by 2 minus 40. Is that good? Are we good? So now we can continue. So this, we can also multiply this 10 with this. So we are going to be having VA. So we're going to be having 3 VA. I hope you are on the same page. This is just the normal math. 3 VA plus 2 VB minus 40 equals to 120. So this is just like over 1. Once we cross multiply, it becomes 12 times 10, 120. So what can we still do here? We can have it as 3 VA plus 2 VB equals to what? 120. If this minus 40 comes to the other side of the equals to sign, it becomes plus 40. So with that, we are going to be having, okay, so let me just continue on the other side. So let's just continue here. So this will be 3 VA plus 2 VB equals to 160. So this is our equation 1. After applying KVL to node VA, we arrived at this equation. I hope that is clear. So let me just create some kind of demarcation here so that we don't mix things up. Alright, so that's equation 1. After applying KVL to the first node. Alright, so before we continue, there's a mistake I want to correct with the sign. So this is minus VB, this will be minus 2 VB. So please let's be careful when you are solving yours. Also be careful with the signs. So this is minus 2 VB, and then minus 2 VB. So this will be minus 2 VB. So in case you saw that while solving, good ones, I've also spotted it. All right, so now this is the correct thing. So now let's continue. Now what we've done to node VA, we are going to do the same thing to node VB. So apply Kirchhoff current law to node VB. So once we do that, we are going to be having something like this. So in node VB2, we also have 2 incoming, 1 outgoing. Is that clear? So the equation there is, this is an incoming, so from here to here. So we are going to be having VA minus VB. VA minus VB is similar to what we are having here. And then minus 20 divided by 5. That is it, then plus. So we already have another incoming current towards VB from the reference to VB. That will be plus. That will be 0. Since it's from the reference, which is 0, then minus VB. So in between we have a voltage source here. So this is plus, this is minus. And in this direction, remember this is the direction here. And it's the same thing as writing it like this. You know, it's going like this, like this. So this is from minus to plus. So that will be plus 10 divided by 5. Are we good? So that is it then. Then equals to, these are just the 2 incoming. So the outgoing, so from VB to the reference, so that will be VB minus 0. So I can just, let me just keep that 0. Let me just write it, VB minus 0. I hope you can still see that. Okay. Then we have, okay, so this is plus and minus. So in this direction, coming from VB to the reference point, we have a voltage source which is from plus to minus in this direction, since it is coming down. So that will be minus 15. Minus 15. I hope you can still see that. Then there's not that, apart, the next thing you have is the 5 ohm resistor over 5. So now let's break this down. So here we are having, so here we can just so just LCM is 5. So we are having VA minus VB minus 20. 5 divided by 5, that is 1. We need to multiply everything here. So we are going to be having minus VB plus 10. If you just want to multiply everything here, this 0 is out. So that's equals to VB minus 0 is out, then minus 15 divided by 5. So if you are finding value in this thing, please give it in this under nodal analysis in this video, please give it a thumbs up. So at this junction we can cross multiply. So if you cross multiply, we use 5 to multiply this, we use 5 to multiply this. So since we are having 5 as the denominator on both sides, they can just both cancel out. Exactly. It saves us more time than cross multiplying and then dividing again. Alright, so now let's simplify what we are having here. So let me just write it out again. So now we are having VA minus VB minus 20 minus VB plus 10 equals to VB minus 15. So now let's rearrange these things to make it look more neater. So we are having VA. I think that's the only VA we are having. Alright, so VA. And then we're having VB minus VB minus VB. If this VB comes to this side, it also becomes to minus VB. So that means we are having minus 3 VB. This is V. Minus 3 VB. I think that's all with the B. So now let's do, then equals to, let's put the numbers at the other side. So you're having minus 15 here already. So you're having minus 20 plus 10. So that will give us minus 10. So if minus 10 should go to the other side, it becomes plus 10. So plus 10 minus 15, that will give us minus 5. And this is our equation 2. Alright, so let's see if we are still correct. Okay. So let me just go through this again to see if everything is correct. Alright, so now we've got our equation 1 and 2. So let me just clean this part so that we can have more space to work with. So now let me just write it out. So we've got our equation 1 to be 3VA minus 2VB equals to 160. And our equation 2 is VA That's just like 1 VA minus 3 VB equals to minus 5. So once we solve this equation 1 and equation 2 simultaneously, we'll get the answer for of our VA and VB. So you can use this is just a two unknown, so you can just use some elimination or substitution method to solve it, or you can use your calculator. So if you want to use the calculator, just like I did earlier when we were doing super mesh, so once you are with your 991 like this, 991 mx, so you press your mode 3 times, you press number 1 for equation. We have how many unknown? We are dealing with 2 unknown, so you press 2 and then this will appear. So for A1 the value is 3, so when you press 3, you press 3 and then you press your equals to. It will ask you for B1, so B1 is the value for B1 is minus 2, so you press minus 2 and then your equals to button. It will ask you for C1, so our C1 is 160, so once you type in 160 and press your equals to sign, so you ask you for A2. A2 is 1, which is this one here. So once you press 1, your equals to, ask for B2. B2 is minus 3, so you press minus 3. Then to ask for C2. C2 is minus 5. So here we have our X is 70 and our Y is 25. So what that means is that our VA is 70 volts and our VB is equals to 25 volts. And with that, we've been able to answer this question. We've been able to get the value of VA and VB. That means the voltage at this particular node is what? Is 70. While the voltage at this particular node is given to be what? To be 25. And we've been able to get those values using what? Using nodal analysis. Using nodal analysis. Now that's it for this example 3. While in that example 4, we are going to be going a little deep into nodal analysis, such that we are not only going to be looking for the voltage at the node, we are also going to be looking for the current in each of these elements that we are having here. Like in the resistor, the question might ask you that, okay, well, find the voltage at the nodes and also the current in the elements, like the current flowing through each of these elements or the resistor, using nodal analysis, because there are other analysis, other methods you can use to solve questions like this. But once a question asks you that and state specifically that use nodal analysis to find the voltage in a particular node and also the current flowing in some of the elements, so how do you go about it in nodal analysis? So that's what I'm going to be covering in the next video, which is example 4. So if you find value in this, please give it a thumbs up. If you have any question or any comments, leave it in the comment section below. And if you are yet to subscribe, please click on that subscribe button. So with that, I'll see you all in example 4.